So modern atomic theory includes this idea that all matter is composed of atoms. And this grew out of observations and laws. The three most important laws that led to the development of this were the law of conservation of mass, which we've talked about, the law of definite proportions, and the law of multiple proportions. Those might seem contradictory, but we'll talk about them. So Lavoisier, we talked about him. He burned things in closed containers. He came up with the law of conservation of mass, and it says, in a chemical reaction, matter is neither created nor destroyed. When you make stuff out of Legos, Lego blocks do not appear or disappear, they just get rearranged. Atoms get rearranged, but they're not created or destroyed in a chemical reaction. The total mass does not change. And this law is consistent with the idea that matter is composed of small indestructible particles. If we combine 7.7 grams of sodium with 11.9 grams of chlorine, we end up with 19.6 grams of sodium chloride. The mass of the two things that we combined is 19.6, and the mass of the thing that we're producing is 19.6 grams. We didn't create matter. We didn't destroy matter. The mass is the same. And we now understand the reason for this. There are a certain number of sodium atoms in 7.7 grams of sodium, and a particular number of chlorine atoms in 11.9 grams of chlorine. And when you combine them in that ratio, you have the same number of sodium atoms, the same number of chlorine atoms that you had before. And so, of course, they have the same mass. Any questions? So late in the 1700s, French chemist Joseph Proust made observations on the composition of compounds. So we talked about compounds, and they have one or more substances that are combined together, right? So he summarized his observations as the law of definite proportions. All samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. This is sometimes called the law of constant composition. So let's look at water. If we take 18 grams of water and we decompose it, one way you can do that is by passing electric current through it, we're going to get 16 grams of oxygen and 2 grams of hydrogen. And if we look at the ratio of oxygen to hydrogen, 16 grams of oxygen to 2 grams of hydrogen, that's an that ratio equals 8.0, or it's an 8-to-1 ratio of oxygen by mass to hydrogen. You can take pure water from any source and decompose it, and the ratio of the mass of oxygen to the mass of hydrogen is always the same, because the composition of the water is the same. And this demonstrates the law of constant composition.
Can you go back one slide?
I can.
Thank you.
And just as a reminder, all of these slides are posted on Blackboard so that you can go back and look at them if you like. And most of these definitions and stuff come straight out of the textbook. Let's do a little example of this. So 2 samples of carbon monoxide are decomposed into their constituent elements. One sample produces 7.2 grams of oxygen and 12.9 grams of carbon. The other sample produces 10.5 grams of oxygen and 7.88 grams of carbon. Show that these results are consistent with the law of definite proportions. So this is a word problem, isn't it? There's a whole bunch of words in there. After we read it through, what do we look for? Look for the numbers. So we're going to pull the numbers out and try to identify what's going on with them. So 17.2 grams of oxygen and 12.9 grams of carbon. That's in the first sample. And then the other sample, so I'm going to write the numbers from the other sample over on the other side. 10.5 grams of oxygen and 7.88 grams of carbon. I pulled the numbers out and I kind of labeled them. Then look at the question. Show that these results are consistent with the law of definite proportions. And we have to say, well, what's the law of definite proportions? All samples have the same proportions of their constituent elements. So what that's telling us is the ratio of oxygen to carbon, you could do it the other way too, carbon to oxygen, in one sample should be the same as the ratio of oxygen to carbon in the other. So I'm just going to take this and divide. Take both sides here. I'm going to find out what the ratio in the first sample is. 17.2 divided by 12.9. So that gives me 1.33 repeating. And so that's grams of oxygen to 1 gram of carbon. That would be the ratio, 1.33 to 1. Then let's do the other one, 10.5 divided by 7.88. And this one gives me 1.33 and a bunch of other numbers, 248,731. That would be grams of oxygen to 1 gram of carbon.
So even if they're different by the numbers at the end, it's still technically the same?
Yeah, so the question is, even if they're different, would they still technically be the same? Well, let's look at them a little more carefully and use significant figures. So here we have two numbers and we're dividing, and so we need to look at the number of sig figs. This one has 3 sig figs, this one has 3 sig figs. So then if we're going to round this 1.33 repeating, that would be 1.33, correct? So with significant figures, that's 1.33. Over here, we have 3 digits and 3 digits, and so this should also have 3 digits. And so when we round this, taking into account significant figures, we actually come up with exactly the same number. If it differed by a little bit in the last digit, I would still say that it agrees with the law of definite proportions. Any questions? So here's an application to life. Vitamins. You can get natural vitamins that they've isolated from plants, and you can get vitamins that were made in a chemical laboratory. Is the composition of the vitamin different if you get it from a plant or you get it by making it in a chemical laboratory? No. The law of definite proportion says vitamin C is the same whether you isolate it from rose hips or isolate it from oranges or you make it chemically in the lab. Now, could there be other trace things that might be beneficial to you that might be present in the organic, the natural vitamin? Yeah, but the vitamin C itself is identical. I think this is a duplicate slide. No, it isn't. Never mind. I know what happened. Okay. That was the law of definite proportions. The law of multiple proportions. 1804, just a few years later, John Dalton, same guy who came up with the atomic theory, published his law of multiple proportions. This says when 2 elements form 2 different compounds, and we're just going to call them A and B, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. Okay, I'm guessing that didn't really make much sense. So what this is saying is, so we've got A and B. We can have A combining with 1 atom of B. We can have A with 2 atoms of B. We can have 1A with 3 atoms of B. They're going to be small whole number ratios. If we think about Lego blocks, so let's say I have one blue Lego block. I could combine that with one red one. Or I could take one blue one and combine it with two red ones. Can I combine it with 1.75 red blocks? Can you have part of a Lego block? No, you can't. You can't have part of an atom either. So the ratio of red blocks in this compound to red blocks in that compound is always going to be a whole number ratio. Here it would be 2 to 1. I think I have an example coming up. Yeah. Carbon monoxide, carbon dioxide. Two compounds of carbon and oxygen. Very different properties. So if we look at the mass ratio of oxygen to carbon in carbon dioxide, it's 2.67 grams of oxygen to 1 gram of carbon. Carbon monoxide, the ratio is 1.33 to 1. 1.33 grams of oxygen to every 1 gram of carbon.
But doesn't it have to be a whole number?
The ratio of this oxygen to this oxygen has to be the whole number. That's a good question. Doesn't it have to be a whole number? The ratio of one, 2.67, to the other is a whole number. 2.67 divided by 1.33. 2.0075, blah, blah, blah. So we would call that 2. The reason it doesn't come out to be exactly 2 is because there's measurements involved. And so nothing's going to be exact. But this is very close to a whole number. With sig figs, it would come out to be 2.01, close enough to round to 2. What this tells us is there's twice as many oxygen atoms in this compound as there are in this one. Carbon monoxide on the bottom is CO, and this is CO2. The ratio of this one to that one is 2 because there's twice as many oxygens in the first compound as there are in the second. Yeah, I already did this. So here's carbon dioxide. The mass of oxygen that would combine with 1 gram of carbon is 2.67. In carbon monoxide, it's 1.33 grams. And we divide those and we get a small whole number. Every time you do this, you're going to get a small whole number, like 2 or 3 or 5 or 7. You're not going to get 19.63 or 2 million. Any questions? Here's an example. Hydrogen and oxygen form both water and hydrogen peroxide. The decomposition of a sample of water forms 0.125 grams of hydrogen to every 1 gram of oxygen. The decomposition of a sample of hydrogen peroxide forms 0.250 grams of hydrogen to every 1 gram of oxygen. Show that these results are consistent with the law of multiple proportions. So we're looking at the mass of hydrogen that combines with 1 gram of oxygen. It needs to be 1 gram because otherwise we can't compare them. So this is 0.125 to 1, and this is 0.250 to 1. So I'm going to take, first I'm going to select my drawing tool. I'm going to take the larger number and divide by the smaller. And what do I come up with? 2. Yes?
Is this pretty much just saying the mass of an atom of oxygen is consistent?
That's the mass of an atom of oxygen is consistent. If that wasn't true, this wouldn't work. Yeah. So that's one of the implications of it, yes.
And you put the 0.250 over the 0.125 because the too far with bigger, right?
Right, you want to put the larger number on top because otherwise you'll end up with a number that's smaller than 1. The only way to get a whole number is to divide the larger number by the smaller. And if we look at the formulas for these compounds, we have H2O and H2O2. And we see for the same number of hydrogen atoms, the H2O2, the hydrogen peroxide, has twice as many oxygens. The mass of oxygen, therefore, is twice as much as in the water. Well, John Dalton is the guy that came up with the atomic theory. And the atomic theory explains these laws. So here are the points of his theory. Each element is composed of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. So this is where all the atoms of carbon or all the atoms of oxygen have the same mass comes in. Atoms combine in a simple whole number ratio to form compounds. So that's where we get our law of definite proportions, and also, by implication, the law of multiple proportions. Atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way that they are bound together with other atoms. Now, this was published in, around 1800, before we knew what electricity was, before we knew about nuclear reactions. And as I mentioned earlier, sometimes a theory needs to be revised a little bit. Question?
It's like the synthetic elements.
Mm-hmm.
Those are made by like adding or removing like I think it's a proton, right? Or is that?
We'll get to that.
Okay.
Yeah, the synthetic elements are made by nuclear processes. Okay, and so like in this last term here, we have the addition of in a chemical reaction. A chemical reaction is different than a nuclear reaction. We know now that atoms are not indestructible. You may have heard of atom smashers. You can smash an atom. You can break an atom into smaller pieces. But it's not something you can do without using a nuclear reaction. So up here when we say tiny indestructible particles, well, they're indestructible in normal chemical reactions. They are not indestructible if you consider nuclear reactions. So it's true outside of nuclear reactions. The second statement, all atoms of a given element have the same mass. Well, now we know that there are actually isotopes, and we're going to talk about those, where the mass is a little bit different. And so this is a statement that had to be modified. Atoms of one element cannot change into atoms of another element outside of nuclear processes. You can change one element into another element, but it requires the use of a nuclear reaction. Okay? So you should be familiar with these ideas. On an exam, I will not say, write the 4 statements of Dalton's atomic theory. I'm not going to do that. But you should understand these ideas.